So hi everyone, I'm Olivia Clifton. I'm a postdoc here in ACOM and MQ. And today I'm really happy to introduce Xiaomeng Jin, who was my peer in the Fiore Amateur Chemistry Group at Columbia. Xiaomeng just received her PhD from Columbia, where she was working with Arlene Fiore. Before that, she received her master's degree from University of Wisconsin-Madison, where she worked with Tracy Holloway, and her undergraduate from Wuhan University. During her PhD work, she had a NASA Earth and Space Science Fellowship for her graduate work, and she also received several AGU Outstanding Student Presentation Awards. During her PhD, she did a lot of work with satellite data, which I'm sure we'll see here, and she was really active in the NASA Air Quality Applied Sciences team and the Health Air Quality Applied Sciences team, which brought together scientists and air quality managers and health managers to use satellite data for air quality applications and human health applications. And now Xiaomeng has just moved to UC Berkeley, where she's a NOAA Climate and Global Change postdoc working with Ron Cohen. And so today she'll be talking about observing the distributions and chemistry of major air pollutants from space. And so Xiaomeng, you can take it away.
Okay. Thank you, Olivia, for your introduction. And hello, everyone. I'm Xiaomeng Jin. And I think I'm going to share my presentation. And or maybe I'll just turn off my video to save some bandwidth. So hello everyone, I'm Xiaomeng Jin. I'm currently a postdoc at UC Berkeley. So today I'm going to present my PhD work working with Professor Arlene Fiore at Columbia University. So the title of my PhD research is Observing the Distributions and Chemistry of Major Air Pollutants from Space. And I would like to first acknowledge my co-authors who are listed here, and also my funding support from NASA Earth and Space Science Fellowship and NASA HCHO. So to start with, over the US, over the past decades, there have been a lot of efforts made to improve the air quality, which led to about 74% reduction of the emissions of common air pollutants. So this progress occurred while the US economy continues to grow, people drive more, and the population and energy use increased, and which is good news, but this is not the whole story. So even with the improved air quality, air pollution still causes the thousands of premature deaths in the US. So PM2.5 and the surface ozone are the two major air pollutants that are associated with a wide range of diseases. So according to the Global Burden Disease Study, ambient exposure to PM2.5 caused more than 80,000 deaths per year over the US. And this number is going down because of the success of emission control. And ozone-related mortality burden is about 20,000 deaths per year, which is much smaller than that of PM2.5. But the ozone-related mortality burden has been growing in recent decades. So now we have two questions. The first question is, how much confidence do we have with this number? And the second is why we see different trends of PM2.5 and surface ozone in terms of their mortality burden. And even though we know that both they are related to anthropogenic emissions. And so these are some motivating questions that I'm going to address in my presentation today. So to study PM2.5 and ozone, certainly we need observations. So this figure shows the county level PM2.5 over the US that are based on available ground-based monitors. And you can see that there is a large spatial variation of PM2.5 across the US. But I also want to draw your attention to the white area where there are no monitors available. And you can see that even for US, there are a large number of counties without monitors. So cellular remote sensing provides a unique view of the world from above, which has the potential to fill in the spatial gaps of ground-based environments. So here I'm showing you the A-Train satellite constellation, which includes 6 sun-synchronous Earth-observing satellites. And among these satellites, I just want to draw your attention to Aura and Aqua, which I will talk about in my presentation. So on board Aura, there is ozone monitoring instrument, OMI, above which they provide retrievals of many important risk trace gases, such as ozone, nitrogen dioxide, carbon monoxide, sulfur dioxide, and formaldehyde. And on board aircraft, there is a modest instrument which provides retrievals of many important environmental variables, including aerosol optical depth that is relevant to PM2.5. So this animation shows the NO2 level observed from OB from 2005 to 2019 over the US. And you can clearly see the NO2 has declined across the US in the past decade, which is a good demonstration of the success of emission control that has been implemented in the past decades. So satellite observations provide a top-down view of the Earth, which measure the total column composition of the air from surface to the top. But the air we breathe in is just a very thin layer near the surface. So it has been a big challenge to link the space-based observations with ground-level air pollution. In the case of PM2.5, AOD is a measure of sum of the light distinctions by all aerosols from surface to the top. But each aerosol particle in the air is unique. It can be either large or small. It can be either sulfate, organic carbon, dust, or sea salt. It can be either water-soluble or water-insoluble. So depending on these properties of each aerosol, the amount of light distinctions by each aerosol particle is different. So what AOD measures is the total of the light distinctions by all aerosols within the atmospheric column. But for PM2.5, we only care about the mass concentration of the small particles near the surface. So the relationship between PM2.5 and the AOD is very complicated. That depends on many factors, including the vertical profiles, chemical composition, and the meteorology. And in the case of ozone, so while satellite instruments can retrieve total column ozone, we know that more than 90% of the ozone resides in the stratosphere that forms the ozone layer. So the contribution of surface ozone to the total ozone is so small that it's hard to detect with current satellite instruments. So with these challenges, now the question becomes, what can we really learn from satellite observations? So my research covers different aspects of ozone and PM2.5, from analyzing the chemical formation and to understanding the long-term trends, distributions, and impacts on human health, and with the ultimate goal to inform the decision-making. So in my presentation today, I will have two parts. So the first part will focus on the right side of the diagram, which is to use satellite-based AOD to estimate human exposure of PM2.5. And the second part of my presentation today will focus on the left side of the diagram, which is to use satellite-retrieved ozone precursors to analyze the ozone chemical formation, and also to make the connections between satellite observations and the ground-level air pollution. We also bring in chemical transport models, geoscan, and the different kinds of the in-situ observations. And this altogether help to understand the source, chemistry, and the impacts of ozone and the PM2.5. So this is a general overview of my presentation today. So now let's get started with part one, which is to link satellite observed AOD with PM2.5 exposure. So there are different ways to link AOD with PM2.5. So the first approach that I would like to introduce here is called the forward geophase approach, in which we use a model such as geoscan to explicitly simulate the relationship between PM2.5 and the AOD. And in general, the chemical transport models can simulate 3D distributions of aerosols. And with this information, and also with some assumptions of aerosol properties, such as size distribution, water uptake, refract index, we could then calculate the modeled AOD based on radiative transfer theory. And then we take the ratio of the modeled PM2.5 over the modeled AOD. And when combine this with satellite-based AOD, it gives us an estimate of satellite-based PM2.5. So this is a forward geophase approach. So another approach is to think about this problem backward using statistical approach. And for the statistical approach, we don't have to know the exact relationship between PM2.5 and AOD. We just treat AOD as a predictor, along with many other variables, such as land use, traffic data, meteorology. And then we build a statistical model, which can be either linear or nonlinear, or maybe based on some machine learning methods. And then we train this model over the ground-based monitors, which could then give us a set of coefficients that can be applied widely to get a full predicted PM2.5 surface. So this is called the statistical approach. In our study, in order to estimate the health impacts of PM2.5 over New York State, we have collected 7 different long-term PM2.5 products. So this include, number 1 is a global geophysical satellite-based product, which is developed by Randall Martin's group at the University of Dalhousie and at that time. And so the global geophysical product has a fine resolution of 1 kilometer, but it's only available at the annual level. And the number 2 is also a geophysical product, but it's only available for North American. And they have made more detailed calibrations at a month level. So they're available at month level. And data number 3 is a machine learning based satellite-based PM2.5 product, which is developed by Yang Liu's group at Emory University. So the machine learning product has fine resolution of 1 kilometer, which is only available over New York State. But the advantage of the machine learning product is that they are available at the daily level. And the number 4 is also remote sensing based products, which is a combination of AQS observations with the remote sensing predicted PM2.5 that is based on a linear regression model. And so this data set is available at the CDC Wonder database and has resolution of 10 kilometers. In addition to these 4 remote sensing based products, we also include 3 non-remote sensing products. So this include number 5 is a fused dataset that combine AQS observations with CMAC model simulation. And the number 6 is based on CMAC model simulation only. And the number 7 is based on ground-based observations only. And we spatially interpolate the ground-based observations using inverse distance reading. So these 7 products, while not exclusive, they cover the mostly commonly used exposure assessment methods for PM2.5. So here I'm showing you the spatial distributions of annual average PM2.5 over New York State from different products in 2002 versus in 2012. And the numbers on the bottom are showing the population weighted average. So the first 3 products have fine resolution of 1 kilometer, and we indeed see that they can capture more spatial details. To compare across different products, and we can see that there are some differences across different products. Overall, the annual population weighted average PM2.5 over New York State vary by about 44%, which is not a small difference. But if we look at the relative change, we can see that all products show consistent decrease of PM2.5 by about 30%. So now, since we have shown the similarities and differences across these products, so the next question becomes, which one is better? So that's been a big challenge to evaluate these products because the AQS observations, which are considered as a golden standard, have already been incorporated into most products at the development stage in order to train a calibrated model. So in our study, we were very fortunate to find some independent observations that are external to the AQS network. And over the urban areas, we use observations from New York City Community Air Quality Survey Program, during which there have been extensive measurements at each neighborhood within New York City. And so the extensive measurements during tests are especially useful to evaluate if these products can capture the detailed spatial patterns of PM2.5 within the city. And over remote area, we found some observations from the St. Regis Mohawk Tribe Air Quality Program, which are located at the northern New York State at the US-Canada border here. So there are 2 SRMT sites. Site A provides data before 2004, and Site B provides data after 2009. And for Site A, its distance to the nearest AQS monitor is about 37 kilometers. But this monitor was discontinued around 2008. As a result, for Site B, its distance to the nearest AQS monitor becomes much further, 130 kilometers. So this coincidentally gave us 2 different situations. The evaluation at Site A is more representative of the area that is away from AQS monitor, but not very far. And the evaluation at Site B is more representative of the area that is far away from AQS monitor. So this table shows the Pearson correlation coefficient between these products and the independent observations. And in over the urban areas, we can see that all these products have limited capability to capture the spatial patterns of PM2.5 within the city. So even though we see that machine learning products show the highest spatial correlation, but we do not see much improvement of these two fine resolution products comparing with these coarse resolution products, especially for the geophysical product. Despite its fine resolution of 1 kilometer, we see a weak correlation between the geophysical product and the CAS data. Over remote area, however, we see that the first remote sensing-based products show higher temporal correlation with the SRMT data than those non-remote sensing products. Which means that inclusion of satellite remote sensing may improve the estimate of PM2.5, at least over remote area. At set A, which is closer to AQS monitor, we found that the machine learning product best captures the temporal variability. But at site B, which is far away from the AQS monitor, we find that now the geophysical product stands out as the best. So using these products, we could then calculate the PM2.5 related mortality burden over New York State. So the mortality burden is calculated as a function of baseline mortality times the attributed fraction, which is a function of ambient PM2.5 times population. So for the baseline mortality, we use the county level mortality rate from the National Center for Health Statistics. And the attributed fraction is calculated based on the relative risk factors, which is based on an integrated exposure response function that has been used in the global burden of disease study. And we include the relative risk factors for 4 causes of diseases, including COPD, RHD, lung cancer, and stroke. And for the population data, we use the county level population data from CDC Wonder database, and then we further spatially distribute this county level population data using the graded population data from CDAC. So this is a method to calculate the health impact of PM2.5. So this figure shows the annual mortality burden due to the PM2.5 exposures over New York State that are using different PM products. And overall found that the PM2.5 related mortality burden over New York State has decreased by about 67% from more than 8,000 deaths in 2002 to less than 3,000 deaths in 2012. And depending on which products we choose to use, the mortality burden could vary by about 28%. But another layer of uncertainties with its mortality burden comes with the uncertainties of the exposure response function. So we simply take the 95% confidence interval of the relative risk factors as a measure of the uncertainties of the exposure response function. And we find such uncertainty to be around 130%, which is 4 times larger than the uncertainties due to the choice of PM product. Okay, so now coming back to the idea of using satellite AOD to estimate PM2.5. So the geophysical and the machine learning approach has their pros and cons. And our evaluation with the independent observations suggests that the machine learning product works better over the urban area, while the geophysical product works better over remote area with few monitors. And another 2 criteria we should also consider are availability and resolution. And in terms of the availability, the geophysical product can be available globally, but the machine learning product is often more limited to the regions with dense monitors. And in terms of the resolution, especially temporal resolution, the machine learning product can be available at daily level. But the big problem of the geophysical product is that they are often more reliable at a longer time scale, such as annual or seasonal mean. So now we may have a question: why is it difficult to estimate PM2.5 using the geophysical approach at the daily level? So if we look at the formula to calculate the satellite-based PM2.5 using the geophysical approach, we can see that it's a function of satellite-based AOD times model PM2.5 over model AOD. And all of these 3 are uncertain. And satellite observations have measurement uncertainties, and they also suffer from the invalid observations due to clouds or snow. And the model, as we know, always have uncertainties. And even though the model is perfect at simulating the distributions of aerosols, when we calculate AOD, we have to make a lot of assumptions with these aerosol properties, such as refract index, aerosol density, site distributions, hygroscopicity. And these are all sources of uncertainties. So in our 2019 ACP paper, we try to follow the geophysical approach to estimate PM2.5 at the daily level. using regional model CMAC over northeastern US. So in our study region, northeastern US, we have luxuries of different sources of observations available, which could then allow us to evaluate the uncertainties from each source individually. So to evaluate the uncertainties of satellite AOD, we use observations from AeroNet. And to evaluate the uncertainties of the model PM-AOD relationship, we use observations from the co-located AeroNet and NQS sites. And to evaluate model uncertainties of the vertical profiles of aerosols, we use the observations from Discover AQ campaign. And to evaluate the aerosol speciation, we use EPA, CSN, and improve data. And to evaluate the model meteorology, especially the relative humidity, we use the radiosonde data from atmospheric soundings network. And to evaluate the model uncertainties of the parameterizations of these factors, we then rely on meta-analysis and conduct sensitivity simulations in the model to test the uncertainties of the satellite-based PM2.5 to these different factors. So these are the basic idea of our 2019 paper. And so I'm not going to go to the very detail of this paper, but I just want to share some lessons we have learned. So the first lesson we have learned is that even though there has been a lot of attention on improving satellite AOD, we found that the uncertainties in the relationship between PM2.5 and AOD could actually contribute larger uncertainties than the uncertainties in satellite AOD. So as I just mentioned, we use AeroNet data to evaluate satellite AOD, and then we use the co-located AeroNet AQS sites to evaluate the model PM-AOD relationship. And then we further scale these errors in satellite AOD using the model PM-AOD relationship and scale the errors in model PM-AOD relationship using satellite AOD. So in this way, these two errors could become comparable with the same unit of PM2.5. So this figure shows the spread of the error in PM2.5 that is attributed to either satellite AOD or model PM-AOD relationship in 4 different seasons. And you can see that not only the mean error, but also the spread of the error is larger for that with model PM-AOD relationship than that for satellite AOD. So now the question is, why is the relationship between PM2.5 and AOD so uncertain? So during the Discover AQ 2011 aircraft campaign, there have been extensive observations of vertical profiles of aerosol mass, light extinctions, and the relative humidity. So using these concurrent observations, we could then further decompose the errors in model PM-AOD relationship into 4 different factors, including column mass, vertical profile, mass extinction efficiency, and the relative humidity. So the way we did this is that we swap in the Discover AQ observed quantities into the calculation of model AOD, and then we replace model AOD with the new AOD to derive a new PM2.5, where one of these factors is replaced with the true observed quantities. And then we look at how this new PM2.5 differs from the original PM2.5, which is just shown. So the figure here shows the spread of the error in PM2.5 that is attributed to each factors. And this figure shows how these errors in each individual factor is correlated with the errors in the total model PM-AOD relationship. And we found that overall, all these factors contribute to some uncertainties. And the vertical profiles overall contribute some positive bias, and the relative humidity contribute to some negative bias. And the negative bias is especially large at high relative humidity due to the hygroscopic growth of aerosols. But in terms of correlations, we found that the temporal variability of the uncertainties in the PM-AOD relationship is mainly driven by the uncertainties in the column mass and the mass extinction efficiency. So to summarize, this is very complicated, and we found that all factors contribute to some uncertainties. But just to make the story more complicated, we also find that satellite-based PM2.5 is also sensitive to the parameterizations of aerosol properties. So in our study, we calculated the model AOD using an offline module called Flex AOD, which could give us some flexibility to vary each individual factors. And so this figure here shows the range of the variations of annual average PM2.5 as we vary each individual factor based on the values that have been reported in literature. And we can see that the size distribution of aerosols contribute the largest source of uncertainty, and the hygroscopicity of sulfates is the second largest source of uncertainty. Other factors have some impacts, but not large as size distribution and hygroscopicity. So this is just a brief summary of my part one. So we estimate 28% uncertainty in the PM2.5 related metal burden due to the choice of PM products, but such uncertainty is much smaller than the uncertainty of exposure response function. And our evaluation with independent observation suggests that inclusion of thermal sensing can improve the representativeness of PM2.5 in remote area, but there is some room for future improvement over urban area. And one of the reasons that it's difficult to estimate PM2.5 using satellite AOD is that the relationship between PM2.5 and AOD is very complicated. But with these multi-platform in-situ measurements, they can be very valuable to quantify the uncertainties of satellite-based PM2.5. So this is my part one, which is on the aerosol side. And so second part of my presentation today will focus on the gas side. And I will talk about how I use a space-based indicator to analyze the chemistry of surface ozone. So ozone, as you may know, that is a secondary air pollutant, which is formed from the photochemical reactions between NOx and the VOCs. So the ozone production is dependent on the relative abundance of NOx versus VOCs. So ground-based observations of NOx and VOCs are limited by their spatial coverage. Thermal sensing provides a unique view of the world from above, which can fill in the spatial gaps of ground-based observations. So even though the satellite instruments cannot retrieve the near-surface NOx or VOCs, for NOx, we can use the satellite-retrieved NO2 tropospheric column density as a proxy. And for VOC, we can use formaldehyde column as proxy, because formaldehyde is the secondary product of the oxidation of many VOCs. And so studies have used the ratio of the formaldehyde and nitrogen dioxide as an indicator of the ozone sensitivity. So in general, a high ratio often means the ozone production is NOx-limited, where the NOx emission reduction is effective. And the low ratio of, on the other hand, often means the ozone production is VOC-limited or NOx-saturated, where the VOC emission reduction is effective, while the NOx emission reduction is counter-effective because of the NOx saturation effects. So this is a basic idea of the indicator approach. So this indicator is simple to use, and basically you can apply this everywhere in the world. But the problem is how high is high and how low is low. That is to find out threshold values to separate the NOx-limited versus VOC-limited regimes. So the first attempt we gave is to use a model, GeoScan, to derive the threshold values to separate NOx-limited versus the VOC-limited regimes. So in GeoScan, we conduct two sensitivity simulations where we reduce NOx or VOC emissions by 20%. And then we look at the surface ozone response to the emission reduction. And since this figure shows the ozone change divided by the emission change as a function of the modeled column formaldehyde O3 ratio, and you can indeed see that the D ozone over DE NOx increases with the ratio, while the D ozone over DE VOC decreases with the ratio. And then we define the NOx saturated conditions as those D ozone over DE NOx is negative, and the NOx limited conditions as those D ozone over DE NOx is positive and is higher than D ozone over DE VOC. And then we look at the probability above which that the NOx limited conditions would occur, and the probability below which that the NOx saturated conditions would occur. And then we draw a line at 95%, which means that for more than 95% NOx limited conditions occur with the ratio higher than 0.9, and for more than 95% of the NOx saturated conditions occurred for the ratio lower than 1.4. From this, we could then give a threshold values as being between 0.9 and 1.4. So this is a model-based approach. But the one limitation of the model-based approach is that what we see from the models may not be the same as what we see from observations. So here, as an example, I'm showing you the seasonal cycle of the modeled versus the OMI formaldehyde O2 ratio in North America. And here we have 4 different OMI ratio because we have 2 retrievals for both formaldehyde and NO2. One is from the NASA group, and the other is from the European chemist group. And so this 4 gives us 4 different combinations of formaldehyde and NO2. And we can see that overall there is some bias between the modeled and the OB retrieved ratio, and the bias could be either negative or positive depending on which retrieval products we choose to use. So this is one limitation, and another limitation is that in this study we use a coarse resolution geoscan model to conduct the simulations, but the coarse resolution model of 2-degree resolution may not be able to capture the urban environment. So in order to overcome these limitations, in our recent research, we built a new approach to derive threshold values that are entirely based on observations. So I think many of you have already seen this ozone isoplot, which describes the nonlinear dependence of ozone production on NOx versus VOCs, or organic reactivity in this case. So this ozone isoplot is generally made from the analytic models. But in our study, what is new is that we are trying to mimic these ozone isoplots based on observations only. So to do so, we collected millions of ground-based observations from EPA EQS network, and then we aggregate these observations according to the corresponding NO2 and formaldehyde, which are sampled from daily OMI observation. And then for given NO2 and formaldehyde, we then calculate the high ozone probability, which is shown as a color in this figure. And you can see that overall, this figure captures the nonlinear patterns of the ozone isoplots. At the low formaldehyde NO2 ratio, which is this area, we can see that the high ozone probability increases with lower NO2, which means that high ozone is less likely to occur with NOx reduction, or is more likely to occur with NOx reduction, which indicates the NOx saturated condition. At high ratio, which is this area, we can see that the high ozone probability decreases with lower NO2, which means that high ozone is less likely to occur with NOx reduction. And in between 2 and 4, when the ozone production is generally transitional, and this is also where we find the highest high ozone probability. And from here, we can give a rough threshold between 2 and 4. But I also want to mention here is that there is no single threshold that we can separate the VOC-limited versus NOx-limited regimes. And we also find some regional variations in terms of the threshold values. And also the threshold values we derived from observation-based approach is higher than the threshold values we derived from model-based approach, which suggests that if we use a model-based approach, we may underestimate the extent of the VOC-limited regimes in urban areas. So now, since we have built a methodology, so the next step is to look at the long-term evolution of ozone sensitivity. So in order to go back further in time, we also incorporate 2 other satellites, including GOM and SCARE-MARKI. So in order to ensure the consistency across these satellites, the harmonization of satellite observations is achieved in 3 steps. The first step is that these products are retrieved consistently under the QA4ECV project that use the same retrieval algorithms and same prior profile. And even with the same retrieval algorithms, there are still some differences in terms of overpass time and resolution difference. So we develop a new method that decomposes the difference across these different satellites into the difference that is due to resolution and difference due to overpass time. And then we further correct SCARE-MARKI and GOM data based on the differences that we derived by comparing OMI and SCARE-MARKI data during the overlapping period. So the harmonization is kind of complicated. I'm not going to the very details of the harmonization, but I just want to share the results that we got from this harmonized data. So this figure shows the summertime multi-satellite formaldehyde NO2 ratio in 7 cities, in 7 US cities in 2 different periods, 1996 to 2000 on the bottom, on the top, and 2013 to 2016 on the bottom. So the blue to green areas are VOC-limited or NOx-saturated, and the brown to white areas are NOx-limited, and in between the yellow areas are transitional. And you can see that in the early period, most cities are in VOC-limited regimes. But because there has been a lot of NOx emission control that leads to a decrease of NOx, we found that the ratio has increased in most cities, which means that these cities becoming more sensitive to NOx emissions. And for many cities, we see that already made transition to NOx-limited regimes in the recent period. And for Los Angeles, New York, and Chicago, while we can still find the VOC-limited regimes in recent period, with the transition from the VOC-limited to NOx-limited regimes have moved toward the city center. So remember, the regime transition often corresponds to the condition where the ozone production is most efficient. And in our study here, we show the locations of three sites where we see the highest ozone in this region. And we indeed see that the locations of peak ozone have moved towards city center in many cities. So to look at it in a more detailed way. So here I'm showing you the satellite-based formaldehyde, NO2, and the ratio as a function of distance to the city center in two different periods, 1996 to 2000 in the dashed line and the 2013 to 2016 in solid line. And here I'm just showing you the Chicago as an example. So as we can see that in the early period, there is a sharp urban-rural gradient of NO2. But this gradient has become smaller in recent periods. But for formaldehyde, we see there is almost no urban-rural difference in formaldehyde. And we do not see any change of and we even see the formaldehyde has increased a little bit in the recent period. So as a result, we found that the ratio of the formaldehyde to nitrogen dioxide, which is the red line here, has become much larger in this recent period, which as a result leads to the regime transition to move from city center from the 120 kilometers away from the city center to around 30 kilometers away from city center. So to connect this with the urban-rural variation of surface ozone, here I'm showing you the summertime average ozone at OMI overpass time, again in two different periods and as a function of distance to the city center. And you can see that over urban areas where the ozone formation is NOx-saturated, we can see that the ozone has increased in recent period in response to the NOx reduction. So further away from city center, where the ozone formation is NOx-limited, we do see there is a large reduction of ozone in recent period. And as a result, we see that there is narrower urban-rural difference in ozone in the recent period. And in the early period, we found that the peak ozone occurred around 120 kilometers away from city center, which is consistent with the regime transition we diagnosed from satellites. And in the recent period, the peak ozone have moved towards city center to around 20 to 40 kilometers, which is again consistent with the regime transition we identified from satellites. From this, we can get a conclusion that satellite remote sensing can indeed capture the spatial and temporal evolution of the ozone sensitivity over US cities. Okay, so over the urban areas where the ozone formation is NOx saturated, the ozone often increases on weekend in response to the NOx reduction. So we call this as ozone weekend effect. So this figure shows the satellite-based formaldehyde NO2 ratio in 5 different periods and in 7 different cities. And this figure shows the difference in summertime ozone on weekend minus weekdays. And you can see that as these cities become more sensitive to NOx emissions, we find that the ozone weekend effect has become smaller and even reversed in many cities. So this figure shows the scatter plots between the ozone weekend effect or the difference in ozone on weekend minus weekdays versus the satellite-based formaldehyde NO2 ratio. And we indeed see there is a moderate correlation between the ratio and the weekend effect. This regression line intersects with 0 at around 3.4, which is consistent with the threshold values we derived from previous slide. So up until now, all our analyses is either based on long-term average or maybe rely on data aggregation to reduce the uncertainties of satellite retrievals. So the daily single observations from these satellites are often noisy and affected by clouds. But in October 2017, the TROPOMI, which is on board the Sentinel-5P, just launched to space. And this new generation of satellite observation have finer resolution and better quality, which has the potential to make the short-term analysis of ozone chemistry possible from space. So just to give you an example, so this is some work that I'm working on recently. And here I'm showing you the troponin retrieved NO2 and formaldehyde over Northern California on November 8, 2018, the day when the California campfire started. And you can clearly see the plumes coming from fires going all the way to San Francisco. And the arrows on the figures are plume trajectories that are at the different altitudes that are generated from the high split model. And the shading represented the plume age. And you can see that the transport of emissions mainly occurs at the higher altitude trajectories between 2,000 and 3,000 meters, which suggests that the campfire injects a lot of emissions into the free troposphere during this big fire event. So this figure shows the day-to-day variability of NO2, formaldehyde, and the ratio in two counties, in Butte, which is the county where the fire occurred, and San Francisco, which is a downwind urban area. So before the fire occurred, the ozone production is NOx-limited in Butte, and San Francisco in San Francisco it's VOC-limited. So this is typical for urban areas in November. But on the day with fire, we found that over the Butte County, there is an increase of both NO2 and formaldehyde, but the increase of NO2 is larger than the increase of formaldehyde, which as a result leads to a decrease of the ratio, which leads to the regime transition from NOx-limited to VOC-limited regimes for Butte on November 8. And on the following days, we see a further increase of the ratio, which is largely due to the increase of formaldehyde, which then bring the ozone production back to the NOx-limited regimes. And in San Francisco has a different story. And before the fire, the ozone formation is VOC-limited. But on the day with fires, we see a large increase of formaldehyde, but almost no change of nitrogen dioxide. As a result, we see the ratio has increased quickly, which leads the regime transition from the VOC-limited to transitional regimes. And on the following days, we see a further increase of the ratio, which then bring the ozone production to NOx-limited regimes on the following days. So of course, there are still a lot of unknowns as how we can use satellite observations to diagnose the emissions and the chemistries from fires. So this is actually my postdoc project that I'm currently working on. But the main message I want to share with this slide is that with this new generation of troponin data, and also with this future geostationary temporal satellites, we may have a better capability to observe the short-term variability of ozone chemistry possible from space. So finally, just to give you a brief summary of part 2. So we show that satellite-based formaldehyde ratio can indeed diagnose the sensitivity of surface ozone to precursors. But I just want to say that the threshold values that separate the NOx-limited versus VOC-limited regimes are very uncertain and also depend on the method we use. But as NOx emissions decline over the US cities, we found that ozone production has become more sensitive to NOx, which means that NOx emission control will be more effective at reducing ozone pollution than it would be, say, 20 years ago. And wildfires emit a large amount of ozone precursors, which leads to a large change of the ozone production regimes over both source and downwind urban areas. But there is still a lot of unknowns to explore in the future, and this is what I'm currently working on. And I'm very happy if you have any suggestions, I'll be very happy to know. And so this is all what I have for today. And thank you very much for listening, and I'm happy to take any questions. Thank you.
So if anyone has any questions, you can ask them directly. You can type them in the chat window. If you're watching through the live stream, feel free to email me if you wish. Anyone have any questions?
I have a question. It's Olivia. So Xiaomeng, in your trend plots in looking at the change in PM 2.5 over New York State, It looks like at the end years there were some increases. Some of the different products were predicting small increases in PM2.5, like CMAC. Yeah, CMAC kind of says in 2011 and 2012 that they were higher. Is that just because of meteorology, and why do you think the other products weren't capturing those small increases?
Yeah, I think it's a good question, but I think I'm not going to overinterpret this trend, because this studies end at 2012, but when I was looking at these following years, there are still some decreasing trends. So I'm not going to say that the PM2.5 began to increase after 2010, but maybe I would just say it's more due to the meteorology, and also maybe there's due to the uncertainties in this model. I think it's mostly the problems with the CMAC model. So I'm not the modelers doing this. So I think this may be due to some model uncertainties, which may be due to the organic carbons, but I'm not sure. But I just want to say that from the observation perspective, we indeed see an increasing trend over time. We indeed see a decreasing trend over time. Maybe I just didn't say it correctly.
Okay, decreasing.
Yeah, it's decreasing. Yeah, yeah, it's not correct.
It's okay. You caught yourself.
So I think I have a question from chat.
Yeah.
From Suyan. How did you calculate the satellite-based high ozone probability? Okay, so yeah, let me go to this slide. So the high ozone probability are not calculated based on cell observations, but calculated based on ground-based observations. So the way I did this, I sampled the ground-based observation, sample cell observations at the locations of the ground-based observations, and then I match ground-based observations with satellite data. And for a given location, and I have like NO2 and formaldehyde. And for giving NO2 formaldehyde, I calculated the all high ozone probability from aqueous observations. So the high ozone probability is defined as a probability of ozone higher than 70 ppb, which is actually the standard. So this is based on ground-based observations, but we do some match between satellite data and the ground-based observations. Okay, so another question is, can you say a few words about the machine learning approach, right? Okay, so this is a slide from Yang Liu, who is the developer of the machine learning product I'm using. But the machine learning product we are using in our study is more complicated than just this figure. But the general idea is that they have we have the satellite AOD and different sources of other observations, other data, such as land use, traffic data, meteorology. And they train this machine learning model over the ground-based monitors, which then could be able to give a set of coefficients that can be applied to get the full predicted PM2.5 surface. So the machine learning model they used in this study is described in Jen Zhaobi's paper in 2019, where they use the random forest model to make these predictions. So this is based on machine learning method. So I'm not sure if I answer your questions, or are you asking about the performance of the machine learning model?
Yeah, I guess that answered all of my questions. I guess more details I can refer to the papers. Great work.
Okay, thanks.
I have a extremely technical question. I don't really know much about air quality research, but the trope-OMI data you were showing, that kind of resolution, what is the sort of file size footprint of this kind of output? that you work with? So is it sort of is this daily data, or is this sort of a blend of different times of day, or just how much data are you actually how much data comes out of TROP-OMI in a kind of sort of regional view like this?
Yes, I think it's a really good question. And for TROP-OMI, so here I'm just showing you an image of a day. So this is one single observation and a daily observation. So the TROP-OMI is on board the sun synchronous satellite. So it overpasses a given place once a day. So this is daily resolution. So it has a daily resolution, and the spatial resolution of TROP-OMI is about 3.5 times 7 kilometers. And so for these files, yeah, indeed, we only have 1 day observation. And here we're just showing this for November 8, 2018. But for other studies, if you are more interested in like more quantitative studies, I have to say that for the daily single observation from TROP-OMI, or maybe from other satellites like OMI, GOM, Skymarky, they have a lot of noises, and they are often affected by clouds. So it's recommended to combine multiple observations together to reduce the noise. But if you want to just look at day-to-day variability, the TROP-OMI already has the capability to allow us to see this. And yeah, I'm not sure if I answer your question.
No, that's great. Thanks. Are there any other questions? Okay. If not, let's thank our speaker, Xiaomeng. And then just a reminder, we're actually going to be having another seminar next week. So keep your eyes posted for the announcement. Thanks, everyone. Okay. Thanks for coming.
Thank you very much.